Special relativity. Developed by Albert Einstein in 1905, special relativity is a theory of physics that describes the behavior of objects when they move at high speeds, close to the speed of light. At these speeds, the laws of classical mechanics and Newtonian physics begin to break down, and strange effects start to occur. For example, time appears to pass slower for an object in motion compared to one that is stationary, and the length of an object appears to contract in the direction of motion. One of the most famous implications of special relativity is time dilation. Imagine two observers, Alice and Bob, who are moving relative to each other. Alice has a clock that she uses to measure time, while Bob has a ruler that he uses to measure distance. If Bob were to pass Alice at high speed, he would see her clock ticking slower than his own clock, because time is passing more slowly for him due to time dilation. Similarly, if Alice were to measure the length of Bob's ruler, she would find that it is shorter than it would be if she were measuring it when Bob was standing still, because lengths contract in the direction of motion according to special relativity. General relativity. Building upon special relativity, general relativity is a theory of gravitation that describes how mass and energy warp the fabric of spacetime. Developed by Einstein between 1907 and 1915, general relativity postulates that the curvature of spacetime is directly related to the distribution of mass and energy in that spacetime. The more massive an object, the more it warps spacetime around it, causing other objects to move along curved paths that we experience as the force of gravity. One of the most fascinating predictions of general relativity is the existence of black holes. These regions of spacetime are so dense and have such strong gravity that nothing, not even light, can escape once it falls inside. Black holes come in various sizes, from small ones formed by the collapse of individual stars to supermassive ones found at the centers of galaxies like our own Milky Way. Another prediction of general relativity is the phenomenon of gravitational waves, which are ripples in spacetime that are produced by the movement of massive objects. These waves can travel across vast distances, carrying information about the source that produced them. Both special and general relativity have been extensively tested and confirmed through numerous experiments and observations, and they form the foundation of modern astrophysics and cosmology. Understanding these theories helps us better comprehend the universe and its many mysteries, from the behavior of black holes to the expansion of the universe itself.